Is a picture of the entire electromagnetic spectrum, and let's take a moment to look at this a little bit. So I want to start here on the right. On the right, I have very long wavelengths, very large wavelengths. So the radio waves begin at hundreds of meters, and they go all the way down to single meters to fractions of a meter. So radio, TV, FM stations, AM stations, they all use waves of this length. Now, if you have a long wavelength, it means you're going to have a very low frequency. Okay, so the wavelength is big, the frequency is going to be small, and you're going to have small energy. That's because just like any other wave, I can say that wavelength equals velocity equals wavelength times frequency. So, since the speed of light is constant and will not change, again, sorry. Let me try that again. So I have the speed, the velocity equals wavelength times frequency. So the velocity is constant, so that's not going to change, which means if my wavelength gets large, then my frequency is going to be small because they're all going to be equal to C. So I don't worry too much about radio waves carrying a lot of energy because they have very small energy. At the opposite then, as I go across the electromagnetic spectrum, we go from radio waves to infrared. Infrared waves are generally given off by warm objects. We can't see them, but they are giving off electromagnetic radiation. In between here, right here, are microwaves. This very narrow slice here in the middle, that is the portion of light that we can actually see, visible light. It is an incredibly tiny sliver of the electromagnetic spectrum. Above the visible spectrum, there's ultraviolet. Ultraviolet light damages our skin and creates sunburns. It can cause skin cancers. X-rays are even smaller in wavelength. And they are used by doctors, of course, they'll go right through your flesh, but not through your bones. So X-rays allows us to make image of broken bones. And the smallest wavelength, which means the shortest wavelength, the highest frequency, and the largest energy, are the gamma rays. These are incredibly energetic, and usually you need things like atoms to be splitting apart in order to make gamma rays. Now, the visible part of the spectrum is important to us because it's what we can actually see with our eyes. So we often remember the order of colors of the visible spectrum by the letters Roy G. Biv. So I see here that red. Oh, let me go back. Red is the longest visible wavelength we can see, about 700 nanometers. And violet is the shortest wavelength we can see at 400 nanometers. 1 nanometer is 1 times 10 to the minus 9th meters. It is a very small wavelength. Okay, so we can move on. Here's another view of the electromagnetic spectrum to give you an idea of the relative sizes of these waves. So radio waves tend to be about the size of buildings and people, which is why radar uses radio waves to see objects such as cars and airplanes and ships. As we get down, a microwave, 10 to the minus 2 meters, is about the thickness of your finger. That's how the length of a microwave. These are, in fact, the electromagnetic waves used in your microwave oven. Because they're only as thick as your finger, That's why if you put a piece of, say, frozen chicken in a microwave and microwave it on high, only the outer centimeter gets cooked, because that's how big the wave is, so it doesn't go any further into the chicken. That's why you have to wait a while for the heat, the heat in the waves in the microwave to heat up the meat, because the wave's not going to go in very far. Infrared, 10 to the minus 5. Visible is, as we said, nanometers, or about 0.5 times 10 to the minus 6 meters. Ultraviolet, X-rays, and the gamma rays, the tiniest. So visible light's about the size of single-celled organisms, which is why when we can use a microscope to look at cells with our eyes. Ultraviolet light is about the size of molecules. X-rays start getting of the order of the size of atoms. So if I want to see individual atoms in an object, I would use X-rays. And if I wanted to see inside of an atom, I could use gamma rays. Now that's very hard to do, but we do use all parts of the spectrum. Even though our eyes can only see this very narrow slice in the visible, we design machines that can help us see all parts of the spectrum. So for example, the VLA radio telescope looks at the night sky in terms of radio waves. The Kepler Space Telescope, which discovered thousands of planets around other stars, looked at light in the microwave and infrared range. A regular backyard telescope that uses mirrors, a Newtonian telescope, just uses visible light, and I can look at the world that way. But we've even created telescopes that work in the X-ray. Chandra looked at the night sky in terms of X-rays. Now, why would you want to do this? Because you'll get a very different view of the universe depending on what wavelength of light you use. Here are some more examples of the different uses of the electromagnetic spectrum. So what you can see depends on the wavelength of the electromagnetic spectrum that you're using. And again, remember, for us, when we say light, we mean any part of the electromagnetic spectrum. Infrared is used for thermal imaging. Warm objects tend to give off electromagnetic radiations in the infrared, which we cannot see. However, we have invented cameras that can see in the infrared. So on these two pictures up here, the blues represent the most infrared, and the red actually represents the least amount of infrared. So if you look at this picture of a house, most of the heat is leaving through the roof and through this window up here. That means perhaps that window is open, or perhaps it was a window that was not replaced. Here is an infrared image of a human body, and you'll see how dark blue your head is, because your brain needs a tremendously great blood supply, so your head tends to be warmer than the rest of your body, which is why it's a good idea to wear a hat in the winter, because you'll help keep that heat from leaving your body. Now, these two pictures are taken of the sun at precisely the same time. This picture on the left here is what the sun looks like filmed in ultraviolet light. The surface of the sun tends to give off a lot of ultraviolet light, and so if I want to look at the surface of the sun, I'd use ultraviolet. Where this picture, which again is taken at the exact same time as the picture on the left, this is the sun taken in using X-ray light. Now, I can't see X-ray, but I can use different types of lenses and sensors to sense X-rays. So the atmosphere around the sun, its corona, tends to give off a lot of X-rays. So if I want to study the corona of the sun, I would look at it in X-rays. Here's what we typically think of X-rays. Here's a picture of an X-ray of a person's head, and because the X-rays have such a short wavelength and high energy, they tend to go right through your flesh, but they don't penetrate the denser bones, and so that's why I get a picture of your bones. Now, even though we can't personally see ultraviolet, it turns out that certain insects do see in ultraviolet. In the early part of the 20th century, it was a bit of a mystery of how bees knew which flowers were ready to be pollinated. So a scientist experimented using ultraviolet paint that just looks clear to us because we can't see ultraviolet, and cameras that can sense ultraviolet. And what he discovered was that what to us just looks like a white flower if you looked at the flowers with ultraviolet filters, the center of the flowers actually look dark in ultraviolet. So unbeknownst to us, the flowers evolved a way to communicate with the bees in ultraviolet light. So when the flowers are ready to be pollinated, the centers of the flowers turn dark in ultraviolet, and that guides the bee to where the nectar is and allows the flower to get pollinated. So we can't see ultraviolet, but a lot of... so let's do some practice. All right, I have two problems here. So what is the frequency of red light with a wavelength of 692 nanometers? So let me turn on, I'll use the yellow pen. All right, so again, I'm going to use the fact that the speed of light is equal to the wavelength times the frequency. Now, I want to find the frequency. So the frequency is going to be equal to the speed of light divided by the wavelength. So I know what the speed of light is. The speed of light is equal to 3 times 10 to the 8th meters. That doesn't change. Not as long as the light's not traveling through a material. If it's just traveling through the air or space, then it's always 3 times 10 to the 8th meters per second. The wavelength's a little bit of a problem, though. The wavelength is 692 nanometers. Well, the problem is my speed is in meters, not nanometers. So I have to get rid of that nano and turn this into meters. Now, this is actually easy to do. All you need to do is remember what the metric prefix for nano is. In this case, nano is 10 to the minus 9. So all you need to do is get rid of the nano and say that this is 692 times 10 to the minus 9th meters. Now, a math teacher might tell you that that's not in proper form, and it's not. You could enter this in your calculator. If you enter the calculator this way, you should always put parentheses around the number or use the EE button. But if you want to make this a little neater, this would also be equal to 6.92 times 10 to the minus 7th meters. Where because I moved 2 decimal places to the left, that's the same. That's the same as dividing by. That means I need to take a 2 away from the power. I'm actually adding 2 to the power, so I move 2 to the left. So I'm multiplying by 100. 100 times 10 to the minus 9 is 10 to the minus 7. If you put that into your calculator, then you would get that the frequency is equal to 4.34 times 10 to the 14th hertz. And there you go. Now, you could also write this in scientific using the EE notation. In scientific, in the calculator notation, this would be 4.34 E plus 14 hertz. The website will understand entering answers in either way. You could enter it this way using times 10 caret 14, or you can use computer speak and just enter it using the E notation. For this next problem, what is the wavelength of radio waves broadcast from WFIG radio, 94.2 megahertz on your FM dial? Well, again, same, it's a wave problem again, so I have the speed of light equals wavelength times frequency, except for now I'm looking for wavelength, so wavelength equals the speed of light divided by frequency. My problem is my frequency this time is not in hertz. So my frequency is 94.2 megahertz. I need to get rid of that mega and replace it with a power of 10. Well, I always remember that if I won megabucks, I'd win $1 million. And so a million has 6 zeros, so mega means times 10 to the 6. So my frequency is 94.2 times 10 to the 6th hertz. And on a calculator, if you use the EE button on your calculator, you could enter this as 94.2 E6. You don't actually need to put the positive in when you do use scientific notation this way. Now again, if you like writing it out fully like this, make sure on your calculator you put all your scientific notation in parentheses so the calculator knows the order of operations. So my wavelength then is going to be equal to 3 times 10 to the 8th meters per second. Sorry about that. Stop. Look at that. What a mess. I'm going to just erase and do this one again. Boom. Alright, so back to beginning. My wavelength is going to be equal to C divided by F. I just said that the F was equal to 94.2 times 10 to the 6th hertz. So the wavelength equals 3 times 10 to the 8th meters per second divided by 94.2 times 10 to the 6th hertz. And you should get that the wavelength works out to be 3.18 meters. And there you go. Okay, so I hope you find this video useful. As you can tell, I'm getting used to my tools. I'm not used to using a tablet to write on the computer screen or to record these talking head videos. This is my first one, so I'm rolling it out. I'll have this posted on YouTube for you to look at home before doing the homework assignment. So after watching this video, you can look at the online assignment and do the problems at the classroom website, mrfig.org. I will also have additional materials posted if you want to open it up and either read it on a computer screen or tablet, or even print them up at home. Okay, all. Welcome to a brave new world. I hope you're all doing well with our stay-at-home orders, and I look forward to hearing from you either through chat or email. Feel free to contact me if you have any questions. Okay, bye-bye.